A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to another video, and maybe you can see it from the paper, but you might have guessed it. It's another episode in the educational exam whatsoever series here on the channel. You guys are kind of enjoying the series, at least this is the feedback that I get, and you want more, and I thought I might as well keep continuing on my calculus exams for now from 12th grade. And this one is about derivatives and a bit of the applications when it comes to graphs and interpreting the graphs. And the title, you might see, is not really clickbait. This test didn't go well. It really didn't go well. Out of 15 Notenpunkte, so grades 1 through 15, I think we got an average grade of 2 or 3. So the students really messed this one up, even though it's not hard. It's just that they really lacked the understanding of the topics at hand. And it's I don't know, as a teacher, you just don't feel satisfied when something like this happened. And maybe they would have gotten a better grade if they would have checked out the contents of today's sponsor, Brilliant. Now, that was a bit of a smooth sponsorship transition, I have to admit that. But in all seriousness, when it comes to interpreting graphs and stuff like this, and just taking a look at visualizations of functions and just concepts in the STEM field in general, Brian does an extremely good job at transferring the knowledge over to their users. Now, if you're not yet familiar with Brilliant, let me introduce you to their services a tiny little bit. Brilliant is an online learning platform and also app with nearly 70 interactive courses in all topics STEM, be it the mathematics that we do today, or maybe it's physics you want to learn, or chemistry, or computer sciences. Really doesn't matter what it is you strive for to learn in the STEM field, Brilliant has a whole lot of exercises and courses up their sleeve that you are certainly gonna enjoy. And students are actually profiting from Brilliant in my classes too. Doesn't matter if it's in 6th grade geometry or maybe 9th grade when it comes to parabolas. I use Brilliant to visualize things like playing around with the parameters and see how the zeros of the functions are going to transform under this parameterization, and just things in general, like showing the interior angles of triangles being 180 degrees in their sum without proving anything, just the visual stuff. It's absolutely fantastic, and if you are a visual kind of learner, if you are a sucker for great graphics and just visualizations in general, and how to get abstract concepts learned in a very tangible manner, then Brilliant is definitely something that I'm gonna recommend to you today. And if you feel like it, you can test it out for completely free, for 30-day free trial, by using my link down there at the top of the description, brilliant.org/FlammyMaths. As mentioned before, totally free access to the whole landscape of Brilliant, and if you feel like this could turn into a long-term relationship, if you are really satisfied with their services and what they can bring you as a user, then make sure to make complete use of my link here down there in the description, and the first 200 people to do so get 20% off an annual Brilliant subscription, which is an amazing deal. They have so much content available on the website, and they are adding so much on a regular basis, it's just an absolute bliss. So don't take my word for it, try it out today. And now we are going to go back to the main video. Once again, thanks to Brilliant for being so kind and sponsoring this video. Now, before we dive into the exercises, just here's the structure of the exam. The first part is without any support materials. It just basically includes checking boxes most of the time and just having a basic understanding of things like continuity, maybe zeros of a function and the like. And there is also a second exercise which doesn't have anything to do with checking, but the students have to decide which of the graphs down there doesn't correspond to a certain function, and they have to justify their answer. This is the first part, and they have 20 minutes to walk through this right here, and then they have to give it to me. And then on part 2, they got 80 minutes for this part. There are support materials allowed, meaning the so-called Tafelwerk, so just the table of formulas and the like, and also, their calculators. First exercise is interpreting a function which is given, and just saying a few things about inflection points and how the graph of the derivative function is behaving. We are going to see about that soon. And the second exercise is a so-called Funktionschar. So it's a parameterized function, a set of functions, and doing some things with tangents there and monotonicity and the like. And last exercise is just straight up doing derivatives using the derivative rules. And if you can't even do something like this, then shit is bound to go down in some kind of way. So without further ado, we are now going to dive into the exercises. And as always, you can find the link to the exam down there in the description, the English version and also the German version. So if you would like to use this in your own studies, or maybe as a teacher, as material for exercising and the like, or maybe you are a teacher too and you just want to use this right here, copy paste as a test, feel free to do so. Knowledge should be accessible to everyone, and this is my way of giving back to everyone out there. And now we are going to dive right in. Feel free to let me know down there in the comments what you think about all of the exercises. Let's go. Alright, let us dive in, and with some editing magic you should be able to see all of the exercises here on the screen right next to me, just like this one right here, 1.1. Let f be a real valued function with a slope of 12 at x being equal to 2. A possible equation of f could be either f of x being equal to 1, x, x squared, x cubed, or x to the 4th power. And obviously, the slope of a function always corresponds to its derivative. This is how it has been defined. So we take the derivative of each and every of those functions. You have 20 minutes to do so. It's very easy. Those are just simple monic polynomials and parent functions at that. And then you plug in x being equal to 2 and see if you get 12 out. So derivative of 1 is 0, doesn't work out. Derivative of x is gonna be 1, doesn't work out. The derivative of x squared is 2x. If we plug 2 in, we get 2 times 2 is equal to 4. Still doesn't work out. But maybe we are getting closer. The derivative of x cubed is gonna be 3x squared. And if we now plug 2 in, we are going to get 3 times 2 squared, which is the same as 3 times 4, which is 12. So we check the 4th box. Okay, let f be the function 27 minus x squared divided by 3 minus x, where x is an element of the domain of the function f. First option, the 0 of f is at x not being equal to 3. So why not plug this in and see what we are going to get? If we plug our 3 into here, we are going to get 27 minus 9 divided by 3 minus 3. Maybe you see a problem here. Obviously, we get a 0 down here in the denominator, meaning the whole thing is going to go to infinity. And I'm a nice teacher overall. I'm very nice. And for the students which are a bit observant, this is going to tell them everything about the exercise. The maximum possible domain of f are the real numbers. Obviously not, because we can plug 3 into here. It explodes to infinity, so we get a singularity here. The graph of f has a horizontal asymptote at y being equal to 3. Meaning what students would need to do here is they would say 3 is equal to 27 minus x squared divided by 3 minus x, and asymptote in that case means we are going to get for x being equal to infinity, that's the horizontal asymptote here, for example, 3 out. This is a limit argument, and for x going to infinity, you are going to notice that it doesn't strive to that, for that value of y, basically. But the next one is going to be interesting. The graph of f has a vertical asymptote at x being equal to 3. Meaning if we plug x being equal to 3 into here, the thing explodes to infinity. Hey, who would have guessed? It's answer D. And the last one, the intersection of g of f with the y-axis has coordinates I, 0, 3. If we plug 0 into here, it also doesn't work out. You are going to get none out. Okay, decide which of the following functions is not defined at x being equal to negative 3. It's just a lame exercise, basically, just plugging all the numbers in. Let us go through the first one. We are going to get negative 3 squared and then minus 9 divided by 3 minus, no, plus 3. No, negative 3 minus 3. And obviously it's defined, it does work out, the denominator doesn't go to 0. Now what about the next one? We are going to get 3 minus 3. No, negative 3 minus 3 divided by 2 times negative 3 squared minus 9. This right here is going to give us 18 minus 9 is 9. It also does work out. What about the next one? We are going to get negative 3 plus 3 divided by negative 3 squared plus 3. Also does work out. We are going to get 12 down here. Now we are getting closer to the end. We are going to have 3 divided by negative 3 squared minus 9. I think we got a winner here. Once again, the number D. Daddy does seem to like the D. It does seem so. So we are going to get 9 minus 9, where everything goes to infinity overall. So it's not defined there. We once again get a vertical asymptote. Now, the following picture shows the graph of a polynomial function f. Which of the following statements holds true? Now, we have basically just an order relation between derivatives, and the derivative here is once again corresponding to the slope. Now, let us just take a look at the graph. The derivative f at negative 1 is greater than the derivative at 1. Now, the derivative f at negative 1 is gonna be negative, because obviously the graph of the function is decreasing, and at 1 it's increasing. It's going to be positive, so this doesn't hold. At 0, the derivative is 0, because right there we have an extremal value in some kind of way. It's greater than f prime of 1. Obviously at 1 it's increasing, so it doesn't work out. F prime of 1 is greater than f prime of 0. Also, what doesn't work out, f prime of negative 1 is equal to f prime of 1. On the one hand, this one is increasing and decreasing the other one, so it also doesn't work out. Same argument as with the first answer. F prime of 2 is greater than f prime of 1. At 2, we have the function being there an extremal value once again. So the derivative there is going to be 0, and at 1 we know that it's increasing. So the order relation here is wrong, and obviously by cancelling out all the other 4 answers, the last one must be correct. F prime of 0 is greater than f prime of 3. At 0, it's 0, and f prime of 3, there it's decreasing, so it's going to be a negative value. So we check the last box. It's not the D, it's the E this time. E, what a great meme. Now, let f be defined as f of x being equal to 2x times x plus 4 squared. What are the zeros of f? And obviously, a multiplication of numbers can only be 0 if and only if 2x is equal to 0 or x plus 4 squared is equal to 0. Or in our case, we're going to get x plus 4 is equal to 0. This is the same argument. Now, meaning our zeros that we are going to get are, we have a double 0, so algebraic multiplicity of 2 at negative 4 if we solve this equation, and also we have a 0 at 0. Meaning the answer is going to be E. What? No, it's going to be the D once again. Negative 4 and 0. Now, that was very easy. Okay, and for the last exercise, let f be the in R defined function x cubed minus x. One of the following graphs, 1, 2, and 3. Oh, I forgot a word there. 1, 2, oder 3. I need to fix this while editing the video. Shows the graph of f. Which of the following graphs do not correspond to f? Students told me here which one corresponds to f. I cannot give any points out. They failed to read the exercise. They just missed out on all the points because they just couldn't read properly. Name them and justify your answer. Now, what about the first graph that we are having? Let us take a look at the zeros of the function here. The zeros of the function are going to be at 0 because we can factorize this into x times x squared minus 1, and the other ones are going to be at negative and positive 1. So all of our functions fit, at least when it comes to the zeros of our function. Now, what students could do, they could plug some values in and see how the function is going to behave basically. Or the other version that they could do is they could, for example, calculate what the extremal values are and also the corresponding y coordinates, finding out where the minimum and maximum of the function are. I'm a fan of just plugging numbers in and just checking, for example, left to our 0, -1. So let's plug, for example, -2 in. So we are going to get -2 cubed and then plus 2, which is going to be -8 plus 2 is going to be -6. So we are basically in the third quadrant there, negative and negative values, meaning automatically number 2 is not going to be it, obviously, because we are dealing next to the, on left hand side to the 0, -1, and we are going to be in the second quadrant. So number 2 can't be it, and this is an argument you can basically use. Now we also have this very sharp boy right here, a pretty sharpy boy. And this sharpy boy can be it too, because polynomial functions are differentiable everywhere. And it just doesn't work out. They aren't differentiable at the sharp here points, basically. So this is an argument that my students are allowed to use. Namely, they are nicely continuous. This function maybe too, but they are also differentiable. And with this function, this just isn't the case. Or, to put it into easy words, polynomials don't have sharp edges. It just is what it is. It's an argument that they can use, and I think that is perfectly fine. Meaning number 2 and number 3 ain't it. And this concludes the first part. Now next up, what we have is a function. In the below picture, we have the graph of a real-valued polynomial function of degree 4. The tangent touching the inflection point W, 4, 18 of the graph, has a slope of -4. Let me sketch out the graph real quick here on the chalkboard such that I can use it. I'm gonna put it here. Give me a second. And the first exercise, sketch the tangent described above into the coordinate system. Now, my students actually did kind of a good job here because they know how to draw a tangent in. Obviously, a tangent, this is just an empirical exercise, must only touch the set point. Okay, so it does not cut it, intersect it in the mathematical sense. But what's also really important is they know the slope of the tangent, -4, and they have a coordinate system given. -4 means we are going to go 4 units into the -y direction and 1 unit to the right. And the coordinate system is scaled a bit, yeah, it's not too nice. Let's put it like this. Only 2 students got it correct because they took a real look at the coordinate system. Meaning if you do that and we got our inflection point here at 4 and 18, roughly here, you have to go from here 4 units downwards and 1 unit to the right, meaning you can sketch the tangent into here like that. Okay, something of that sort. Obviously it doesn't look good right now because it's on a chalkboard and it's not the best way to draw graphs, to be fair. This is one of the downsides. Okay, and that's basically it. There's not much more they need to do here. Justify that the graph of f does not have any additional inflection points outside of the shown part of the coordinate system. Now here is an argument that they can use. A polynomial of degree 4 has maximum 3 extreme points, meaning it does have only 2 inflection points at most. 1 inflection point is already given, but where's the other one? Obviously it's here and it's a saddle point, but this is not something that they can argue with right now because obviously you can't be certain if it's a saddle. It can have a slight slope. You don't see it right here perfectly. But what they can make use of is a curvature argument, meaning if we have 2 inflection points and at most 3 extreme points, we have a change in curvature 3 times overall. The first change in curvature is going to be up here. We have a right curvature. Then down here we have a left curvature, and this is going to change right here into a right curvature once again. 3 curvature changes, 2 inflection points in here. And that means, because it's a fourth degree polynomial, we have reached our maximum of inflection points. And that's it. State the values of the two zeros of the derivative function f prime of f. Now, what are the zeros of the derivative function? This is where the slope of our original function is going to be 0. Now, if we take a look at our graph, they just need to work with the graph here. We have a saddle point here, basically. This is the argument that they are supposed to use. Meaning, what we get right here is we have our first one here, meaning this is right here going to correspond to a 0 on our derivative function f prime. And also the saddle right here, where we have a horizontal tangent, is also going to correspond to some kind of 0 of the derivative function. Our derivative function is going to be a third degree polynomial because our original function is a fourth degree polynomial. And if we sketch this into here, for example, what you are going to notice is that our function is at first strictly increasing up until this maximum, meaning our derivative is going to have positive values up until here. It's going to look something like this, really doesn't matter. Now it's going to cut through the axis here, and then what's going to happen is we are going to have a maximum somewhere or a minimum in some kind of way. Obviously, we are going to have a minimum because our function is going to be decreasing at first, where our inflection point was. So somewhere here. Then what's going to happen is our function, our derivative function is going to have a minimum here, and then it's going to be increasing once again up until we reach the saddle, where we have an algebraic multiplicity of 2 of our derivative function, or no change in sign, and then it's going to go downwards once again. Meaning, overall, the zeros of our derivative function are going to be, on the one hand, if you read it in the graph, it's going to be 2. This is for our extreme point here, our maximum, and also we have the saddle right here, supposedly saddle, and this part is going to correspond to x being equal to 8. So we got 8 right here as the second one. 2 and 8 are the answers. The graph of f prime has a minimum. Name its coordinates and justify your answer. Now, if you have sketched this out, then it's already rather easy, because what you already have given by those arguments are going to be the x value of the minimum of the derivative function. Namely, it's going to correspond to the x value of our inflection point. So in this case, the exercise says it's going to be 4. Now, what about the y-coordinate? This is a bit of a nifty one, because here the exercise, it says that the inflection point is at 418, and most students are going to say, well, the minimum is going to be at 418. Obviously not. If you take a look at this sketch right here, don't forget what the slope of the tangent line is. The slope of the tangent line is going to be the y value of our derivative of the function at that certain x value. And this is going to be at 4, meaning what we have right here is going to be the coordinates of our minimum at, this is going to be 8 and 4 here of the derivative function. Did you find this tricky? My students did. I'm not certain about that, but it is what it is. Okay, next exercise. It's one that I also really like. Let fk be the set of an R-defined functions with fk of x being equal to negative k times x, x minus 8, where k is element of the positive real numbers, but without 0. So positive but not 0. Calculate all the zeros of fk. And this is very easy because I'm a nice teacher. It's in a nice form. A product of two things can only be 0 if and only if one of the things is equal to 0. K is non-zero, meaning x is going to be equal to 0, or x minus 8 is going to be equal to 0, meaning we are going to get x being equal to 8 here, or x being equal to 0. And then we are done. And I can tell you something, only like 2 students or 3 students max got this one right. And this says a lot, honestly. Show that the point 4 and 16k is the maximum of the graph of fk. How can you show something like this? Obviously by using differentiation. We are going to differentiate this function right here. I'm going to rewrite it just for my convenience a tiny little bit. Fk of x is equal to negative kx squared plus 8 times k times x. We are going to differentiate this, so fk prime of x is going to be equal to negative 2 times k times x plus 8 times k. Not x, k. And as mentioned before, we are going to take a look at the zeros of the derivative function because the slope at a maximum is equal to 0. Now, obviously what we are going to do is we are going to add this part on both sides. So we are going to get that 2 times k times x is equal to 8 times k, and dividing both sides by 2 times k, you can do so because k is not equal to 0. We are going to get that the extreme value of x is going to be equal to 4. And this is, I think, the x value that we are looking for. Also, we need to show that it's a maximum. So what we are going to do is we are going to differentiate it a second time. So f double prime of x is going to be equal to, if we differentiate this, we are going to get negative 2 times k. And this right here is obviously less than 0 for each and every k because k is positive, meaning it's going to correspond to a minimum. No, maximum, because it's less than 0. I'm definitely sorry, I'm being stupid here. Now, last thing to do is to find out the y value, and we do this by plugging 4 into our original equation that we got up here, meaning fk of 4 is going to be negative k times 4 times 4 minus 8. 4 minus 8 is negative 4. Negative and negative is positive. 4 times 4 is 16, so 16k, meaning our extreme point is going to be at 4 and 16k. And this is what we had to show. Now, show that the graph of fk does not have any inflection points. And this is so easy. And seriously, no one got it, apart from those 2 or 3 people. But it's so easy. To check if something has an inflection point, you are going to take the second derivative and set it equal to 0. But k is non-zero, so it doesn't work out. Or, obviously, because we don't have an x in here. Another argument which I would have graded, right, okay, this would have been fine with me too, is it's a fucking parabola. It only has one maximum. You can see this right here. So it can't have any inflection points and doesn't change its curvature. Being a teacher is frustrating at times. Next exercise. Show that the graph of the function fk is always increasing at x being equal to 2. This is also basically a gift to the students because they don't really have to do anything because they already calculated the derivative and now they plug 2 into here. So fk prime of 2 is going to be equal to negative 4 times k plus 8 times k, resulting in 4 times k. And 4 times k is greater than 0 because k is greater than 0. Meaning it's increasing, obviously, and we are done. And last but not least, calculate the equation of the tangent t of f2, so we plug 2 into our k, at x being equal to 2. So at first we write out what f2 of x actually is. If we plug 2 into here, what we are going to get is negative 2x times x minus 8. Obviously, we need to find out what the slope of our tangent is going to be, meaning we are going to differentiate this bit, f2 prime of x. And we know what f prime of x is. This is this thing. Plugging 2 into here, we are going to get negative 4 times x plus 16. And if we now plug 2 into here, because we want to check at 2, it's so stupid easy, because we already have fk prime of 2 given here. We are going to get 8 out, obviously. So f2 prime of 2 is going to be equal to 8. I'm such a nice teacher. And students just don't understand it, that I'm being such a nice fuckboy. I'm a math fuckboy, and they just don't understand it. They don't understand how easy that is. If I look at this now, it's just so... It's so underwhelming, and I don't understand how they can fail so miserably. It's seriously beyond me. Now we got that tangent has the equation now 8x plus n. And the last thing that we need to do is find out what the absolute lead is, the y-intercept of our tangent. How are we going to do this? Well, we need to find out what the y value is that it shares with our original function. We need to find out the Berührpunkt where they do touchy-touchy and kissy-kissy, you know, just with their lips touching each other, just a tiny little bit. So what we are going to do is we are going to plug 2 into this equation right here. So the next thing to do is f2 of 2 to calculate this. What we are going to get is negative 4 times 2 minus 8. What we are going to get is this right here is negative 6. We are going to get 24 out. I think, yeah, 24. So we know 2 and 24 is what they are sharing, and now we can plug this into here. So t of 2 is going to be equal to 24. It's going to be equal to 8 times 2 plus n. 8 times 2 is 16. Subtracting 16 from 24 is going to give us 8. So n is equal to 8, meaning overall the equation for our tangent is going to be 8x, not x. I'm being German here. X! With a slight German aggressiveness packed onto it. 8x plus 8. And that's about it. And the last thing to do, I think I can fit it onto here. Please forgive the mess, but I think this should be fine with you guys. You know me, okay? You know Papa Flammy. Calculate the first derivative of the following functions. The first one is x divided by x minus 1 squared. What we are going to do, obviously, is we are going to rewrite this a tiny little bit. Namely, f is hence equal to x times x minus 1 to the negative 2. And if we differentiate this, we are going to make use of the product rule. So x is going to vanish. So the first part is x minus 1 to the negative 2. And then plus x is going to be preserved. Then we are going to differentiate this part. We are going to make use of the chain rule, obviously, meaning we are going to drag the negative 2 to the front. X minus 1 is going to stay. We are going to reduce the power by 1, so negative 3. Obviously, the inside derivative is going to be times 1, and that's it. They don't even need to simplify it. They can just leave it like this and just call it quits. Now, the next one is going to be g being equal to 4x then z to the 4th power minus ax squared plus 4a squared. And you can probably guess what most of the students did wrong. Nearly everyone. They also differentiated a. They got it right on the middle term. They left a alone. But on the last term, why not differentiate a too? I don't get it. Meaning if we were to differentiate this, then we are going to get that g prime is equal to 16x cubed minus 2ax. And the last part is going to vanish, obviously. Okay, next up, we got the volume formula for our good old sphere. And, well, if we were to differentiate this with respect to r, v prime of r, we are going to drag the 3 to the front. 4 divided by 3 times 3 is going to give us 4 times par times r squared. And that's it. It's that easy. Now, next up, we have h of x being equal to 3x squared times 2 minus x cubed plus 6.9. There's always a 69 somewhere in my exams and a 420 in some kind of way. Now, obviously, this part right here is going to vanish, so that's the easy part. You already get a point for that, if you notice this. Okay. Other than that, we just make use of the product rule. Yeah, this is what you should do here, obviously, and the chain rule. So the first part, the x squared differentiated is going to give us 6x times 2 minus x cubed. And on the second part, we are going to preserve the 3x squared and differentiate this. We are going to drag the 3 down, so times 3, and then times 2 minus x squared. And taking the inner derivative of 2 minus x is going to give us -1. As mentioned before, they can leave it how it is. And last but not least, once again, Zusatz, I'm going to leave it like this. It's called bonus exercise, obviously. We have our boy, the mass divided by the volume, obviously. It's the density. And we are going to rewrite this. The density with respect to the volume is going to be equal to m times v to the -1. And differentiating this is actually fairly easy, obviously. We are going to track the 1 down, the -1. So negative m times v to the -2. Yeah. And that's it. That was the test. And in my opinion, it was ludicrously easy. Like, there was, apart from the exercise with the tangent and the 4th degree polynomial, I can understand this if they get it wrong. But the exercise with the set of functions right here, the parameterized one, I have no idea how someone can fail this. Everything is so nicely structured in my exams. I pay so much attention to detail. And they just don't understand it, that they are structured in a way that everything is built upon another. Even this exercise, if you draw this right here, you get the D exercise for completely free. So yeah, it just is what it is. You rage as a teacher from time to time, but I hope you got a kick out of it and you found this exercise cool and this test cool. And let me know what you think down there in the comments below. If you think that this was overkill, maybe too easy, what I could do better. And yeah, as mentioned before, use the test to your heart's content. And if you want to support the channel, check out Brilliant and also support the channel on Patreon if you want to keep it alive. And up until next video, I wish you guys a flammable day. Please stay safe. See ya.